So, very good evening. And now, today we are going to continue with the discussions of the previous shortest path algorithms. So, last class, we have already discussed the shortest paths over directed graphs, but we have seen various situations. Assuming the graphs are always directed, we have discussed certain logics. First case we have seen when the graph had no negative edges, no negative weight edges, and cycles could exist. So if that kind of a graph existed, we have used effectively de Dijkstra algorithm. That solution we have seen. Then we wanted that if negative weight edges exist, what to do? So we had negative weight edges allowed. But in lieu of that, we needed some criteria to solve the problem. And then we had a cyclic graph. So in that case, we have used the DAG shortest path algorithm. And then we have another situation where negative weights also allowed and cycles also can exist. So we need a solution for such problems also. So for this, the solution is known as Bellman Ford Algo. So we are going to see Bellman Ford algorithm. But the main logic we have to now plan. In case of a de Dijkstra, I could easily say that a main logic was possible that just 1 second, let me have. So the main logic in case of a de Dijkstra, we could say that lightest edge could be chosen or lightest vertex could be chosen and stepwise on each step. So that on each step, the distance was finalized for the lightest vertex and that was okay. Fine. This was final. In case of DAG, the TS order helped us and order-based vertex was finalized immediately on each step. One vertex finalized every time. And then we proceeded because once no incoming edge to that vertex was remaining out of uncovered vertices, so we could say now this vertex is final and whatever possible relaxations were there, they have been considered. And because the directional edges were being considered acyclic, so if I said that this vertex over, it means all incoming edges to this have been already covered. And all incoming once covered, that means no further relaxation will be possible. And then we can proceed further cyclic graph. So it said that was the main logic. Now, what should be the main logic? Because earlier, this was a kind of, I normally call as an optimal choice possible at every step. And this was guaranteedly optimal, hence okay. Normally, we call this as a greedy choice. Once we talk of greedy algorithms, we will discuss. But what about for Bellman Ford? We don't have such possibility because neither we have possibility of having the lightest vertex. Negative weights can further make it further lighter, nor we have a cyclic graph and the cycles exist. So TS ordering also don't exist. So now for Bellman Ford, the logic has to be effectively that we have to probably try for all possibilities, try for the worst possibilities of relaxation. Means worst possibility means maximum relaxations possible could be attempted to be tried. So how to get those maximum relaxations? That is what we have to think. So I say, in this case, the assumption for Bellman Ford is also there that negative weight cycles don't exist, negative weight edges can exist. cycles should not exist, and then my assumption will help me in making some attempt of maximum worst possibilities or relaxation possibilities. Negative weight cycles mean what? It will be clear that if I have a cycle, let's say node 2 to node 3, and 3 to back, this weight is, let's say, 3, this is -4. So I can say 2, 3, 2 is a cycle, and cycle's weight is 3 minus 4 minus 1. So this is a negative weight cycle. And I say this can create problems. The problems will mean actually because of this, solutions can become infeasible, or solution becomes infeasible if negative weight cycle exists. If negative weight cycle exists, solution becomes impossible or infeasible. Why? Let's have an example. Say I have vertex 1. I reach to vertex 2, let's say with a distance of 5. Assume that there is this connection also available, 3 and -2. So even if I say 1 to 2 is shortest for the time being, assume that 5 is the shortest compared to all other routes, any other routes, other vertices. But then I say it is possible to have a path named as 1, 2, 3, 2, and still it becomes reaching from 1 to vertex 2, but this will have the total weight as 5 from 1 to 2, then 2 to 3, 3, then -4. It becomes a 4. You could see it further reduced, but that indirectly creates a problem that now I can have further a path like this. I reach 1 to 2, but having cycle again repeated. So I say 1 to 2, 2 to 3, 3 to 2, again 2 to 3, 3 to 2. That will be 5 plus 3 minus 4 was once done. Again, it will be done 3 minus 4 again. It will become 3. Infinite use of this cycle can lead to minus infinity as the distance among 1, 2. Among path 1, 2. So that effectively means the solution becomes practically infeasible. So we say negative cycles or negative weight cycles can lead to infeasible solutions. So my Bellman Ford algo, I'll say Bellman Ford algo, what it will do is negative weights are allowed, negative weight edges, okay, negative weight cycles, if at all exist, find and report error. Or I'll print that infeasible solution. So I will do that. Otherwise, the shortest paths are to be found for all pairs or for single source shortest path. So this is what I need. So Bellman Ford allows this all except for situation of negative cycles, and negative cycles obviously create a problem which leads to infeasible solutions. So now the question is, what we said was we wanted the logic to be developed. So I said, think of maximum possible relaxations. And if there are no negative cycles, only then maximum possible relaxations are countable. Negative cycles mean infinite relaxations. And hence we said, don't go for this. So with negative cycles, infinite relaxations possible. And obviously this doesn't become a solution. So not used. Not possible. Then if no negative cycles. Then what are the maximum possible relaxations? Let's find out that answer. So I say maximum relaxations will depend on what can be maximum number of edges in a path, in any path. Then if I say there are V vertices in total, then can you tell that from any vertex U, or I'll say some vertex U to small vertex V, what this path maximum edges can contain? Well, the answer is probably in your mind, but I'll explain. Maximum will mean, say, path covers all vertices. And of course, repetition of any vertex means no use, because cycles are always positive. Repetition of vertex is of no use. Any vertex, if repeated, effectively means a cycle is being used. So, for example, I say, I want to go to from vertex 3 to vertex 6. So, path could be 3, 1, 5, 4, 2, 6. If total 6 vertices were existing, then this can be the maximum lengthy path. Beyond this, if I say there is some path like 1, 5, 1, 4, 2, 6, effectively means it's a cycle. And a cycle means a positive weight. So this means out of this, there is no use to go from 1 to 5 and then to 1. From 1 directly, you could go. This means 3, 1, 4, 2, 6 is better path. And shorter, because the cycle has no use. So compared to this will be better, hence no repetition of the vertex needed. So that means the lengthiest path might be having all vertices. All vertices. If all vertices cover, directly or indirectly mean clearly that there will be n minus 1, or to be called as a v minus 1 edges. Obviously, because all vertices are covered, so to connect all vertices in the path, v minus 1 edges. Like if I said, in the earlier case, I said 3, 2, 5, 1, 4, 6. So v is a 6. So this is one edge, E1, edge 2, edge 3, edge 4, and edge 5. So 5 edges needed, obviously. So 5 edges are the maximum. Now I say, so what I will do, I will do the relaxation is for maximum times possible. And that will be the logic. And maximum time is obviously v minus 1. It will cover all possibilities of relaxation for every pair or for every requirement. All possibilities of reducing the distance, effectively reducing the distance means going via another vertex. All those will get covered, and every time I'll be going for another vertex being covered, and through this process I'll be able to relax the distance or reduce the distance. So effectively, if I say that I have to talk of one line logic, so I will say main logic is now simple. I can say that effectively I'm going to do nothing but I'm going to relax the distance based on edges. Obviously, we do the relaxation of the edges. In the books, it says relax the edges, but effectively that means relax this. How? Progressively using, so I say progressively will mean I will repeat it multiple times, decreasing the estimate progressively decreasing the estimate, say V dot D, V dot distance for each vertex V corresponding to edge UV, each edge UV. So corresponding to each edge possibly, I will reduce estimate, again reduce, V minus 1 times reduced. And this progressively effectively means till distance is final. And I claim that after V minus 1 iterations, it is guaranteedly final, because no further relaxation will be possible. All possible edges on that route have been considered. Having said that, through an example, it will be more clear. So let me just show you the example. So let's say I have this graph. I have taken the same graph from the book. And for this graph, if I see, let's say I have source vertex as 5. Intentionally, I'm taking a last vertex number. So my V is equal to 5, means 4 iterations will be needed. And I'll show how 4 iterations will help me. So corresponding to this graph, I'll just save it and show it the graph again, so that we are not able to get disturbed again. I'll just put it at the last after certain this. And so here I have this, and now I'll show the corresponding implementation and discussions. So I say, I have got this, and here 4 iterations existing, and that will be finalized. So effectively, if this is the graph, I'll say my Bellman Ford logic is simple. Whatever I have written the main logic, using that logic, I'll explain that source will be informed to me. And using that source, I will be, of course, doing something. So initialization, etc., I will do. Initialization effectively means your predecessor to be initialized for everyone, your estimate or your distance to be plus infinity for everyone, predecessor to be minus 1 for everyone. That is it. So this is your vertex available. So you have a predecessor, and you have distance, and you have the adjacency list. Nothing else needed. No PQ needed. No, nothing else needed. So this graph will be still sufficient the way it was sufficient for DAG implementation. Implementation done. Obviously, after that, I have to say source distance to be equal to 0. Initially, it is infinity. It is indirectly equivalent to saying that in the graph at index SRC, the distance is stored. So I am making that distance to be 0. This is syntax, but I'm not going into the syntax anymore, so you can understand. Just I showed you that this is equivalent to this. Now, what I said is repeat V minus 1 times. So what I have to repeat? I said what I have to repeat is all edges to be considered for relaxing every vertex. So effectively, that means I will say for each edge UV in the graph, every edge for all adjacent vertices. So every edge of every vertex to be considered. And if relaxation is possible, that means if a V's distance is greater than the distance via U, that means effectively U's distance plus weight of UV. So this becomes effectively the distance via U, via vertex U. If this distance is going to improve my estimate, this is my current estimate. If this can be further reduced, so effectively I am going to do the relaxation of V's distance using edge UV. That is what we have just written in one line logic, and this is what it means. But effectively, my logic is over. Effectively, the algo is complete. How? Let's see over the graph and understand that. So for the time being, I have this graph. Let me just change the pen color so that I'll be able to explain it in a better way. So corresponding to this pen color, I say, if I have got the corresponding SRC as this, then correspondingly, I am supposed to have the path to be identified and relaxation to be done. So currently, this distance is 0. I'm writing everybody's distance here. This is infinity. This estimate is infinity. This estimate is infinity. This estimate is infinity. Now, based on this distance as infinity, you are supposed to improve the estimate via relaxation. So if I say all pass one means all edges to be covered. All edges. What way? Let's say I go adjacency list order. Anyway, you can go, but let's assume I go adjacency list order based. Means, first of all, I'll go through this adjacency list. So this adjacency list has corresponding certain edges, then certain edges. So all edges are listed here. So I say, can edge 1, 2 means corresponding to 1, can this edge do some relaxation? Edge 1's weight is infinity already. So infinity plus minus something has no meaning. So effectively, edge 1 will not make, vertex 1, any edge will not make any difference because infinity plus 2 will make some impact, no use. Once has got correspondingly this outgoing. So this also, if I try to consider infinity minus 7 will affect the 2's distance, again of no use. So effectively nothing done. Similarly for vertex 2, 2's outgoing, this not of no meaning because already 2's distance is infinity. Infinity minus 2 leads to again infinity, no use. So everyone will be considered, and later for vertex 5, the corresponding adjacency list will be considered. Corresponding to 5, I have got this. So in pass 1, my edge 5, 4 edge will change the distance for corresponding vertex 4. 4's distance will become now, instead of infinity, 0 plus 7. So that is, this will become effectively 7. Similarly, this vertex is also, this edge is also considered from 5, and this is 3, 0 plus 6, 6, this is 6, 0 plus 6. So this will become overall 6. So 3 is the distance also relaxed. In pass 1, 2 distances get relaxed. So this becomes a 6 and this becomes a 7. So this pass 1 over. Then starts pass 2. Pass 2 means again all edges is considered. So again I will change the pen's color to have another different color and show you the different kind of coverage of this. Let's say I will make it green now. So I say pass 2 will mean again I am going to start with first adjacency list of vertex 1. So vertex 1 adjacency list, let me just see where is my pen. Yeah, here. So this will be covered. Correspondingly, this is one vertex, 2, 7, 2 and minus 7. 1 is currently already infinity, infinity minus 7, no use. 1 then it has a 5, connectivity with the 5, infinity plus 2, but it is already 0, nothing to be done. So this also not considered. Then next edge covered, Next edge is 3, edge 2, 3. From 2 it is going. Vertex 2 I have got here. So 2, 3 effectively mean that I have this particular edge. 2, 3 is this edge. So this edge has got some improvement possible or not will depend what is the edge 2's contribution, already infinity, and this side is lesser. So effectively nothing done. Then edge 3 considered. Edge 3 has vertex 3, 2. This is vertex 3, 2. So from vertex 3, 2, I can see this is my vertex 3. This is my vertex 2. 3, 2 means this 5. So this 5, 3, 2, this vertex is going to make the change, and 3, 5, 3, 2 vertex has weight 5. So edge 2 is getting, or vertex 2 will get a relaxed distance. Earlier it was infinity. Now instead of infinity, it will become 3's distance plus 5. 3's distance is 6 plus 5. This becomes 11. So this will get changed to 11. And I will have this value in pass 2. So my effectively 2's distance will improve through this process and it will become 11. Similarly, 4's adjacency list will be covered. Corresponding to 4, if I see the correspondingly one is this, it is a 9. So this is a 7 plus 9. So obviously this becomes a 16. 16 means this will be over. So edge 1's distance also changed. So 1's distance also changed. Then 4's outgoing is this also. I will be attempting by this edge. Every edge is being considered. So 4's edge cover considered. 7 minus 3, it becomes 4. So via 4, it becomes 7 minus 3 equal to 4. So 11 will also be modified. This will further become 4 in pass 3 itself. So in pass 2 itself, earlier it became 11. And now further from 11, it will be modified to become 4, like this. So 2's distance gets further improved. After 4, 5's, similarly 4 has any more outgoing? No. So after 4, 5's edges will be considered. 5's edges, can this further relax? No. Can this further relax? No. Second pass over. Second pass over, then similarly pass 3 will come. So pass 3 will start. Again, all edges covered. Considered again. And this consideration will further lead to further relaxations. So if any relaxation via some indirect edge now possible, that will be done. Similarly, pass 4 will be done. And I say now final. After pass 4, I can claim that result distances are final. And they are the shortest. The claim has a simple logic that all possible edges or all possible routes, all possible paths, all possible edges in the path have been considered. Indirectly, you can also think other way. You can think in terms of indirectional or incoming edges also. Ultimately, any vertex has maximum n minus 1 incoming edges from a distinct vertex, which is not covered again and again. So n minus 1 incoming edges. This distance can be relaxed via all of this in one after the other. So maximum in minus 1 incoming edges and minus 1 edges exist. All can also relax, say in an order that they keep on relaxing, but maximum v minus 1 iterations are sufficient. Maximum v minus 1 edges possible. So maximum these many relaxations are this. and no negative cycles, so maximum relaxations will get completed. Knowing this, effectively, I can say that this means I'm able to find. But I also said that I should be able, so let me correct my pen color. So I said, now I want my negative cycles detected also. But we have not yet detected if exist. So I say how to detect. So I'll say one more pass can help me. I'll say, so initially whatever for repetition I did v minus 1 times in the previous logic, I have done my Bellman Ford algorithm. And here I have already written whatever. So I said repeat v minus 1 times. And here I have done some relaxation, etc., etc. Now I say go for one more pass. I will say again do for each edge belonging to in the graph. If I'll say each edge means each edge UV. So I'll have each edge UV in graph. If V's distance is still greater than U's distance plus weight of UV, it means further relaxation is possible, and that means effectively negative cycle exists. Why I claim? I'll explain. And solution not possible. So this is no solution possible. This I can have extra, and through this I will be able to claim this for negative, for detecting negative cycles. Why I am saying this? My claim is simple that after, I'll put on the next slide, after v minus 1 iterations, maximum v minus 1 edges have been covered. Maximum edges that were v minus 1 covered in the path. If path is further improving, additional edge coming to the path, coming and relaxing and reducing the distance means what? Additional edge coming and reducing the distance means some vertex will be repeated. Because another edge coming, so all vertices are already covered. Some vertex repeated means cycle being used in that path, cycle being used, and cycle leading to reduction in distance. It is leading to reduction in the distance means that negative cycle exists. Because for certain node, that negative weight cycle exists only because of that distance of some vertex can get further reduced and cycle is leading to that. So extra iteration can confirm that. And hence I will say through extra iteration, I can check this particular process. Having said that, let's wind up, and now it is clear that you can easily use this. Just go for the time complexity of the Bellman Ford. So here it is Bellman Ford. So let's see the time complexity. Effectively, time complexity is very simple. Your initialization, of course, order of V, repeat V minus 1 times. So effectively, it means order of V. Within this nested, this is going to be E times each edge of the graph, clearly meaning that this overall executes order of V into E times. V minus 1 or E effectively means order of VE. So whether you say V minus 1 into E, or effectively this is V minus 1 into E, effectively meaning this becomes order of VE, because for each repetition, for each pass, all edges are being considered. So that are E edges in the graph. So my total time complexity is straight away order of VE. And obviously, time complexity will be higher because the negative weights also exist, cycles do exist. So in simple choice or simple decision on every step was not possible. When every step's decision is not possible, nesting has to be used, and that will lead to the total additional time complexity. So with this, I'll wind up and I'll say implement this. Again, I'll give you the main purpose, that implementation of this Bellman Ford via both alternates you must try. Use the corresponding adjacency list also, adjacency list representation, or use adjacency matrix representation. Pseudocode is similar, so for both you can try. I'm sure you will be able to do this, and that will give you a great confidence if you have implemented all of this. Bye-bye, all the best. Best of luck to all of you. Let me stop the recording now.